Hey everyone, welcome back to Calculus 2. This will be lecture 15 of the course. And so in this we're going to switch gears a little bit and we're going to start working on integration techniques again. Okay, and so we've been looking at applications of integration, and then we had a brief stint with differential equations. And so in this section, we're going to move back into developing some integration techniques and, some very important integration techniques, and then also just some more theory about integrals in general. And so we're going to start out kind of relaxed and get into some basic integration rules and I guess this is a strangely titled perhaps, but basic integration rules, and also some more like kind of tricks for doing some integrals, right? And this won't be by any means a comprehensive list of the tricks, but it'll kind of get you started on how to handle some not so straightforward integrals. Okay, and then after this section in lectures 16, 17, and so on, we'll get into more integration techniques like integration by parts, and then using trigonometric integrals and that kind of stuff. And so we'll get into some more material, more techniques in a moment. But then this section is going to be kind of an easy intro to thinking about more complicated integrals. Okay, so let's go ahead and get started. We'll call this section. Oops, let's put a little ink on here. We'll call this 3.1, and that will be basic integration techniques. Okay. Okay, so as I said, so this section will explore techniques that can be used to expand the set of integrals for which our basic rules can be applied, right? And so really integration is an art as much as it is a science, and it's not as straightforward as differentiation. I think I've said that before, and probably you're detecting that already. But really kind of knowing which integration rule to use is pretty key, but it can be very challenging, right? And so what we're going to do is we're going to kind of roll with that idea for our first example. Our first example will be a comparison of three similar integrals. Okay, so three similar integrals that, though they look similar, they have very different. The way we calculate the integral, the way we do the integration, is very different. Okay, so here are our examples. So part A is this guy, the integral of 4 over x squared plus 9 dx. The second one we'll look at is the integral of 4x over x squared plus 9 dx. And then the last one is we'll just throw another x in the numerator. 4x squared divided by x squared plus 9. Okay, so these are all obviously very similar, right? They, vary one another by just the addition of a single x variable in the numerator of the integrand, right? This is 4, this is 4x, that's 4x squared. But that slight variation causes the integration technique that's required, the integration rule, to be totally different. Okay, so let's start with part A. So in part A, we can basically use, for this guy here, we can basically use the arctangent rule. Right, so this is an arctangent. This has the form of the arctangent, right? So for this one, we'll use the arctangent rule, right? And here we'll let u equal x and a equal 3. All right, so if that's the case, then we'll just write this out quick. This is x squared plus 9 dx. Right, and so just going through this, we would pull the 4 outside, and then we would have x squared plus 3 squared dx. Right, and so if again, say letting u equal x and a equal 3, we get 4 times the integral of 1 over u squared plus a squared du. And so this is the exact form that we expect when our antiderivative is the arctangent function. And so we can just kind of recall what that is. It turns out that this integral is 4/3 times the arctangent of x over 3 plus c. Okay, right, so in this case, the 4 up top is basically just a constant, pulls out front, and you have this 1 over u squared plus a squared format. And that calls for the arctangent. Okay, so again, this first example is only an example to show you how different the integration rule can be for integrals that are very similar, right? And so for the first example, it was arctangent. What happens with the second example? Right, well, the second example, let me just rewrite it here. Second example is 4x over x squared plus 9. And so this is a u substitution, right? You can see if you let u equal x squared plus 9, then du is 2x dx. And so you can manipulate the constants in the integral to come up with an appropriate substitution. So here we'll use a u substitution. Okay, so we'll let u equal x squared plus 9, then du is 2x dx, and so that means du over 2 is equal to x dx. Okay, and so that's the basic idea here. And so we can go through this, and we would say, what would we say? So we would pull the 2 out front here. Actually, we don't need this part. We can just do it with this. So this is 4 already, so we'll just pull 2 of them out, factor the 2 out, and we'll have 2x over x squared plus 9 dx. Right, and so the bottom is u, the top 2x dx is du. So this would be 2 times the integral of 1 over u du. Okay, and so that integral is twice the natural log of the absolute value of u plus c. So we get twice the natural log of x squared plus 9 plus c. Now, of course, that's always positive for all x. And so we get 2 times the natural log of x squared plus 9 plus c. Okay, so that is what this one evaluates to. So obviously very different from the previous example. So just tossing in that one additional variable of x causes these functions to have totally different integrals. And what about the third one? The third one is, so for part C, the integral is 4x squared over x squared plus 9. Okay, so it's that guy. Now, in this case, a u substitution will not work, right? So remember, if you let u equal the denominator, then du is 2x. So you'd be sitting with an extra x somehow up here. And so that's not helpful. And so we have to do something totally different. All right, so in this case, you are able to manipulate the integrand using polynomial division. So we can use polynomial division to rewrite the integral. Okay, all right, so kind of did that already off to the side, and when you do that, you get this integral. You get 4 minus 36 over x squared plus 9. Okay, so this is what you get when you basically divide x squared plus 9 by 4x squared. And the reason you can do that, you can do that is because this numerator polynomial is as large as the denominator, is of this a degree equal to or greater than the denominator polynomial degree. Right, so this is a second degree polynomial, this is a second degree polynomial. Right, if this was a first degree polynomial, you couldn't really do it. Right, but the fact that it's a second degree polynomial or higher means you can use this division technique, and it's very often useful. Right, but this makes all the difference because now we can break the integral up into two parts here. Like so. Right, and then this part here is a straightforward integral, and then this one here looks a lot like the first integral we did, part A, where we're going to use the arctangent. Okay, so we can run through this, and we would get 4x for the first one minus 36 times. Now this is going to be, so here basically your a is 3 again, and your u is x, and so the arctan would be the form. So you get 1/3 arctan of x over 3, and then the whole thing plus c. Right, so you would end up altogether here with 4x minus 12 arctan x over 3 plus c. Right, so again, a very, very different result from the previous examples. Right, so I guess it's sort of similar to the first example in that it has an arctangent in it, but very different from the second one for sure. Okay, so here's what we got for the first one. Here's what we got for the second one. And then this third one, very different. Okay, so that's just a little, that's just a quick example to show you just how different the integration can be depending upon the integrand. And two integrands who look very similar, two functions that are real similar, may have very different, may evaluate to totally different integrals, right? So, okay, so for our second example, let's talk about an example where we use two basic rules to solve a single integral. Right, so sometimes we'll need to use more than one integration rule to solve an integral. Right, so here's an example. The integral from 0 to 1 of x plus 3 over 4 minus x squared. Square root of that. Okay, so something like this. Right, so this kind of an integral, you see that numerator where you've got x plus 3. It's very common when you have something like that to want to break the integral up into two separate integrals. And that's indeed what we're going to do here. So you have the integral from 0 to 1 of x over 4 minus x squared plus the integral of 3 over 4 minus x squared. Square root, right? So you can break it up like that. And so for this first part, we can use a u substitution. Right, so basically letting u equal 4 minus x squared means that du is equal to 2x dx, which we can negotiate with this numerator. The second one is the 3 can come outside, and it'll be 1 over the square root of 4 minus x squared. And so this would be like 2 squared minus x squared, which is like a squared minus u squared square root. And so this guy fits the arc sine rule. Okay, so two totally separate integration texts being kind of used in the same setup here. So for this first one, let's kind of do some of the side work here. So we'll let u equal 4 minus x squared, then du is equal to negative 2x dx. Okay, and so that's what we'll use in this part here. And then this other one, kind of off to the side, just keeping track of the fact that these are different, let a equal 2, u equal x, then this is going to be a squared minus u squared. Okay. All right, so that's that one, that's that one. Okay, and so we can come in here and we can sort of write this all out. All right, so this first one, we need this -2 up top. And so we'll divide by -1/2, or divide by -2. And we'll rewrite this as -2x over 4 minus x squared dx. And that'll get us the total substitution that we need. And then this one here, we'll pull the 3 out, and then this is going to be 1 over 2 squared minus x squared square root. Okay, and so that perfectly fits the form of the arcsine. All right, and now we can go ahead and make all those substitutions. And this becomes 1 over the square root of u du plus this guy. Well, we'll just actually do it. This would be the arcsine of x over 2. Okay, put the plus c on there, knowing that we haven't quite done this one yet. But so then this one we can finish up, and it becomes, so this is u to the -1/2, and so the integral there would be u to the 1/2 over 1/2, and then you've got this part here, just like that, right? Okay, so we've got all of the pieces in place here, and now we just need to come back through and do some cleanup, resubstitute things back in. And so when we do that, let's start by writing the u as 4 minus x squared here. And so this is, let's see, so that would be 2 times the square root of 4 minus x squared. Okay, so that's what you get for this front part. And then plus 3 arc sine x over 2 plus c. And so this kind of cleans up a little bit, and we get what, like negative square root of 4 minus x squared plus 3 arc sine of x over 2 plus c. Okay. All right. Excellent. And I think actually this was a definite integral, wasn't it? Yeah. So it started out as the integral from 0 to 1. We kind of dropped it and turned it into an indefinite integral. But let's put that back in and finish it up. Okay. So that means this here is integrated from 0 up to 1. And so we get rid of that. This goes up from 0 to 1. Okay, and then from 0 to 1. Okay. So sometimes that can happen. You're focused on kind of getting the integral solved, and you sort of forget what you're doing. Okay, so yeah, so we plug in 1 for everything here, and we get, let's see, this will be negative square root of 3 plus 3 times the arc sine of 1/2, and that turns out to be pi over 2. Okay, kind of looking ahead at that. And then you're gonna, so that's everything evaluated at the top, and then at the bottom, this would be negative square root of 4, which would be basically a -2, and then the arc sine of 0 is 0. Okay, so you get this. And this is a big old mess. Let's just crank out, a real number for this, and we get 1.84. Plugging it in, that's what you end up with. Right? So the point of this example was not really to look at, the definite integral side of it, but just for completion. I couldn't let it not get done. But the point here is that, this integral started as a single integrand, and you can break it up into 2 parts, and each part will require in this case, required a separate integration rule or integration technique. In the first case, first part of it was u substitution. Second part of it used an inverse trig function, right? So it fit the form of the arc sine in particular. Okay, excellent, excellent. So that's something you come across all the time. Okay. Here's another example. This one is one that people haven't seen. I think maybe that first example, I think we've seen that before. That's come up in examples. But this is one that probably hasn't come up in examples. And this is going to be where we use a substitution that's a little bit different. Okay, so in this case, we want to evaluate the integral of x squared over 16 minus x to the 6th, and this is the square root. Okay, and so notice that this radical here, this 16 minus x to the 6th, that can be written as 4 squared minus x cubed squared. Okay, and where we're heading with this is that this is going to fit the form of an a squared minus u squared square root, and that's gonna lead us to the arc sine, isn't it? Okay, so we can do a u substitution, right, where we let u equal x cubed, and then du is equal to 3x squared dx. Okay, so this is kind of, we're going to be combining a u substitution with this trig, with this arc sine form. Okay, so we have the integral of x squared. Let's just rewrite here so we have everything. So we have this. Okay, and then we're going to rewrite this denominator in this format. So that'll be 4 squared minus x cubed squared. Okay, and if we let u, as we said, let u equal x cubed, then du is equal to 3x squared dx. And so we're very close, aren't we? Right? If we were to do this, right, that gets us really what we need. This would be 4 squared minus u squared in the bottom. The top would be 3x squared dx, which is du. Okay, so let's make the substitution. And so this would be 1 over 4 squared minus u squared. Okay, and this is just the a squared, right? That's the a part of it. And so this fits the form of the arc sine. And so this would be 1/3 times, and then the integral is arc sine of u over 4 plus c. Okay, and so that's very clever, right? That's a very clever technique, right? So you're basically, this doesn't work as written, as it doesn't work for the arc sine, but we can do a u substitution here. I mean, it doesn't work because of the denominator, but it also doesn't work because of the numerator. But with a clever u substitution here of x to the 3rd power, we can capture the top and fit the format of the arc sine. Okay, so that's a very nice technique. I don't think this one comes up a lot, but it's just something to keep in mind, that you can do this kind of thing as well. Right, so that's the whole point of this lecture, is just to show you some like kind of tricky types of integrals that you may see, that you may come across if you're working through a textbook or some homework or something. All right, very good. That's a great example. Let's take a look next at another thing that can happen. It does happen quite a bit, and that's going to be when the log rule is required, but it's not obvious how it would work. So you could call it a sort of disguised form of the log rule. Okay, so the integral here would be, that we're interested in, is the integral of 1 over 1 plus e to the x dx. Okay, so something to note with this guy is if we let u equal 1 plus e to the x, right, then du is equal to e to the x dx. So given this, I mean, this wouldn't work as a u substitution, right? So basically what this implies basically a direct u substitution does not work. Okay, so that would be kind of, maybe you would throw in the towel at this point. But what we can do is we can manipulate the integrand just doing like what you'll find is a very basic integration technique here, or a very basic algebraic technique. It turns out to be something rather powerful and allows us to integrate this, right? So if we start with the integral of 1 over 1 plus e to the x dx, okay, and then we integrate, then basically take the same thing, but in the numerator, let's add and subtract e to the x, like so. Obviously, we haven't changed the overall integral, right? This is still just, we added something and subtracted the same thing, right? But now we have new opportunities that we can set up here. So what we want to do here is the following. We're going to split the integral apart into this. So we have the integral of 1 plus e to the x over 1 plus e to the x. All right, and that's obviously going to be equal to 1. And then we're going to subtract off the integral of e to the x over 1 plus e to the x. Right. And in doing that, so this one is just the integral of dx. But then over here, we've got basically what we need to do just the standard u substitution that we tried initially. Right? Initially, we said, oh, let's let u equal 1 plus e to the x, then du is equal to ex dx. Oh, but we don't have an ex dx here, so it wouldn't work. But by just doing this little algebraic trick of adding and subtracting e to the x, now we have the setup we need. This we can obviously integrate. This part here we can use the u substitution. Okay, so we've got the integral of dx minus, and now this is just going to be what? 1 over u, isn't it? Right, so e to the x dx is the du, and 1 plus e to the x is the u. So this would be minus the integral of 1 over u du. And so we can integrate this, and we get x minus the natural log, the absolute value of u, plus c. And of course, u is 1 plus e to the x. So we get x minus the natural log of 1 plus e to the x plus c. Sorry about that. And so that is the integral. Now, of course, this is always positive. This 1 plus e to the x is always positive, and obviously 1 is. And so I guess we could drop the absolute values and write it like this. Okay, but there you go. Right, and so this is a kind of a simple thing that you can keep in mind. It's very often beneficial to, keep your algebra tricks handy, right? So here we just added and subtracted the same thing, and that allowed the integral to be calculated easily, just using rules that we've seen. Okay. Great. So similar example. This is a disguised form of the power rule. Right, so let's look at this one. We want to evaluate the integral of cotangent of x times the natural log of sine of x. So kind of a beast to look at, kind of a tough one to think about. But let's see here. So one of the things we can do here is we can let u equal the natural log of sine of x. Okay. Then du right? So you'd have to use the chain rule on this, and it'd be 1 over sine of x times the derivative of sine of x. Du would give you cosine of x over sine of x, okay, which is equal to the cotangent of x. Okay, so here you have all the setup for the power rule, right? So this would be, let's rewrite it here. So I've got the cotangent of x times the natural log of the sine of x, right? And so you can sort of think about the cotangent, sorry, that should be cotangent dx. So cotangent dx is du, right? So that takes care of that part and that part, and then u is the natural log of the sine. So this is the integral of u du, which obviously we can handle, right? So this is just going to be u squared over 2 plus c, right? So you get what, 1/2 times u squared, which is the natural log of sine of x, okay, plus c. There we go. Okay, so this one was, the power rule could be applied, but you just had to, be willing to kind of think through, what is the derivative of natural log of sine x? Not a super easy, not a hard derivative. It's a chain rule derivative, 1 over sine of x times the derivative of sine of x. And then you had to note that cos over sine is cotangent, and so that gives you the rest of the substitution. Okay, so kind of, again, a tricky one, kind of a nice one. So just because something looks really convoluted on the surface, if you start messing with it, start looking for substitutions, it's very, very often the case that you can find one. All right. Another example, and this example will be a trig identity. So this is actually the last example, but for this section, this is going to be, very often. I mean, many of you, if you're taking calculus, calculus 2, most of the time you've taken a pre-calculus course or like a trigonometry course, and trigonometry certainly comes up a lot in calculus. And so here's an example where just kind of remembering the trigonometric identities that you struggled through in trig can be very helpful in calculus. Right, so let's evaluate the integral of tangent squared 2x dx. So you see that tangent squared, and you may think to yourself, oh, wasn't there a Pythagorean identity that made use of tangent and secant possibly? We all remember the sine squared plus cos squared equals 1, but what about the tangent and secant? Well, there is one, and it's that tangent squared theta equals secant squared theta minus 1, right? So that's the other Pythagorean identity from trig. And so that one we can use to evaluate this trig identity, or sorry, this integral involving a trig function, right? So the integral of tan squared 2x dx is going to be equal to the integral of secant squared 2x minus 1. Okay, so that's nice. So these trig identities, these trig functions have the same values. You can swap them out. Okay, and so this obviously can be broken up into two pieces. All right, so we could write this as, hold on, let me think about this for 1 second, make sure this isn't. Let's think about the u substitution first. So we're going to need a u substitution for this interior piece. So let's let u equal 2x, then du is equal to 2 dx, right? Okay, so let's rewrite this as 1/2 times the integral of secant squared 2x minus 1 times 2, right? So 1/2 times 2, right? So that's all just 1 dx. Okay. And then, yeah, so that gets us all the substitution we need, right? So 1/2 times the integral of secant squared u minus 1 du, and then we can break it up into two pieces if we like. Right, so we could break it up and make it 1/2 times the integral of secant squared u du minus 1/2 times the integral of du. Okay, and then this guy here, the integral of secant squared is tangent. So this would be 1/2 times the tangent of u. Okay. And then this one over here is just the integral of du, so that's just u. Okay, plus c. Right, and then u in this case is 2x, isn't it? And so this is 1/2 times the tangent of 2x minus 1/2 times 2x plus c. And so we could clean this up, and best answer is probably 1/2 tangent of 2x minus x plus c. Okay, and so that's a great place to stop with that integral. Nothing else to be done there. All right, so these have just been a few examples of different kinds of integration techniques, different tricks that can be attempted when the integration isn't totally obvious. Okay, and so I do want to spend just a second sort of kind of summarizing this a little bit, right? So basically, procedures for fitting integrands to basic rules, right? So these are things you can try, basically. So as I said, integration is not like differentiation. It's similar in some ways, but in other ways it's quite a bit more involved and challenging. And it's not obvious when you see an integral, like how to solve it. You know, when you have a derivative, it's usually pretty obvious how to differentiate it. I mean, if it may be a complex derivative, and it might not be obvious, may not be easy, but it's usually like no mystery like how to proceed. Integrals are a different story. Like they frequently can be, you know, a little bit like how best to proceed is not always obvious, right? And so if you've got an integral, you're trying to solve an integral, and you can't seem to figure out which rule works or what to apply, you can try to manipulate it. And here's just kind of a short list of things to try. All right, so maybe the first thing would be consider just expanding the numerator. Right, sometimes this is obvious, right? So like if you have something like this, 1 plus e to the x squared, try expanding it and see if it looks different, right? So like this could be expanded to 1 plus 2e to the x plus e to the 2x, right? And it may turn out that this is very integratable, whereas this may not be, right? So just basically expanding the numerator, and this is relatively obvious. I think most people would try that. Another one that's kind of obvious but worth putting on the list for sure is separate the numerator. Okay, so example here, we've seen this a number of times. 1 plus x over x squared plus 1, for example. Right, this is just an example, right? But anytime you have like multiple terms in the numerator, you can split it apart. This can be written as 1 over x squared plus 1 plus x over x squared plus 1. Right? And again, just rewriting the integrand like this means it may be much easier to integrate. Something we talked about previously, but that's not something we've done a ton of examples. We'll see more examples of it coming up, but that's completing the square. There are a lot of integration rules that require like an a squared and a u squared, some combination of the two. Maybe it's an addition, a squared plus u squared, a squared minus u squared, or reverse, right? And so just being able to complete the square can be very helpful sometimes in assessing, when a form like that can be used. So say you have something like this, 1 over 2x minus x squared, that whole thing, square root. This doesn't look like an a squared minus u squared kind of integral or integrand, but if you complete the square, this can be rewritten as 1 minus x minus 1 squared, right? And then this certainly does look like an a squared minus u squared. If a is 1, u is x minus 1, you've got it, right? And so this would fit a trig. This would fit an inverse trig rule, right? I don't remember which one off the top of my head, but one of those would fit here. Okay, and so this is just, again, completing the square. Okay, and then another one we saw tonight was dividing rational functions. Right, so even if, upon dividing a rational function, you don't get, maybe the two functions don't perfectly divide, that doesn't mean that it's not helpful. Even with the remainder, it can still be helpful, right? And so we saw an example of that earlier where we had something like this, and then upon doing the division, x squared, plus 0x plus 1 divided by x squared, you would do the division and you would, end up with something like this, 1 minus 1 over x squared plus 1. Okay, and so yeah, you could, this as an integral is easier to deal with than this as an integral, potentially. Okay, and so that's a great trick to keep in mind. Now, dividing rational functions is actually super easy. If it seems like it's really hard to you, just go back and review, like pull out a college algebra textbook. It's always covered in those books. And, or pull out a pre-calculus textbook and you'll find a section on dividing polynomials. And that's all you need. That's exactly what you need. And just go through a few examples and you'll see, oh, this is actually it's a lot like long division of, actual like integers and things. So pretty straightforward. Okay. The next one is one that we use tonight. That's the old add and subtract terms in the numerator trick. Okay, so that's a trick that, we use tonight. But for example, if I have something like this, right, if I do 2x plus 2 minus 2 up top, right, then I can rewrite this as 2x plus 2 over x squared plus 2x plus 1, and then, minus 2 over x squared plus 2x plus 1. And so that gets me a nice u substitution on this part, which kind of wraps in the x. And then this part, we can just use, we can use a different technique on, right? But the problem with the u substitution here is that du here is going to be equal to 2x plus 2. And so you can get to that using this trick. Right, and then we saw the example tonight with the sort of hidden log rule, right? And so, like with the e to the x, right, where we add and subtract e to the x. So another good example of this being useful. Trig identities. Always keep trig identities in mind, right? There's about a gazillion of them. And they're very often useful if you have something that involves a lot of trigonometric functions. And so simple things like cosine squared x plus sine squared x equals 1 can be used. Or something like what we just saw. Or, there's double angle formulas, there's half angle formulas, there's power reducing formulas, all kinds of things in trigonometry, right? You spend like a third of the semester just looking at trig identities. So there's lots and lots of them to choose from. And something to keep in mind. Okay, and then the last one that I'll mention is also kind of a staple from algebra. That's the the trick of multiplying and dividing by the same factor. And I know we've seen that with integrals already, but multiply and divide by the same factor. When this can very, very often be useful. All right, so let's say you have 1 over 1 plus sine of x. You could change this integrand into 1 over 1 plus sine of x times 1 minus sine of x over 1 minus sine of x. Okay, and when you do that, you get 1 minus sine of x on top. And what do you get on the bottom? You get 1 minus sine squared of x. Okay, and here comes a trig identity. This is the cosine of x, cosine squared x. All right, and so this can all be rewritten as like secant squared x minus sine of x over cos x, cos squared x. Right, and this can be gotten. This is just the tangent when you integrate, and this is I think you can do a u substitution here. Okay, and so again, this can be integrated. This, I'm not sure how you would integrate directly. You'd have to do some kind of a trick to it. Okay, so very good. So again, that was just kind of a quick, kind of an easy, not easy, well, kind of a gentle introduction to some more advanced integration techniques. And then next time we'll talk about integration by parts. It's an extremely powerful integration technique. One of, probably the best ones that there are. Well, they're all great, but this is a pretty good one. So we'll leave it at that and talk to you all next time.